Hello? Okay, so let's continue. So what we are going to be doing in this class is that we are going to be getting into circuits for the next 2 weeks, which is this week and next week. Is one of the most important weeks because that's when we are going to study series circuits, parallel circuits, and combination circuits. Um, uh, that's going to be, as you can see by I mean, once you do the next test, as you can see by the course outline, not the course outline, like the instructional plan, that's going to be worth 25%. So you got to make sure that you can commit enough time this week in order to be prepared to write your test next Friday. Okay, so but the most important above all is to be able to go through all these circuits and to grasp the concept of what a series circuit is, a parallel circuit is, and also what a combination circuit is. Okay, so um, one tool that I want you to be able to use, okay, so it's called Falstad. So if you go to Falstad, okay, let me see if I get the right one. Okay, so when you go to Falstad, then you can see a simulation and the little yellow dots, and we are going to do one of those today. The little yellow dots indicate the way that current flows. I think it's very useful to be able to see what's happening in a circuit, how is the current flowing, and to be able to measure all the different inputs and outputs from a given circuit. Like in this instance, and that's what we are going to cover today, okay? We have a circuit here. And as soon as I close my switch, we have a series circuit. You can see that you start to observe this flow. These little yellow dots indicates the flow of current. So this is going to be one of the tools, or this is going to be the tool that I want you to use the most. Because let's say, like, if I give you any given circuit, let's say that I give you a circuit like this, and I ask you, can you please tell me that if we had a voltage of 10 volts, you see what I did? I just double click on the power source. I'm going to do it again. Double click on the power source and double click on the voltage, or I can just do a single click and backspace, and then I write 10 volts. The thing that I have to make sure of is that it's DC, that the waveform is DC, because I can have AC. And you can see that as soon as I click on AC, right here at the bottom on the oscilloscope, the waveform is going to change. I can have a square wave. And again, it's going to change the waveform, okay? However, in our case, we are just dealing with DC, so that's what we are going to use, and we can either apply or just press OK. If we apply, we can leave everything open, and we can change any of these parameters. But the only parameter that we are going to use for our class is going to be voltage, and we are just going to leave it on the DC waveform. So I'm going to click OK here, and then if I think that it's a little dizzying to see the current flowing so quickly, right here on this control here, on this slider, I can control the speed of my current. So I'm going to slow down my current a little bit. And now it's going to be much easier to see how your current flows. Now, something which is important to keep in mind, this is the conventional flow of current, okay? Because this is an electronics simulator, but it's an electronic simulator that we can use, in DC for simple circuits as well. Now, in this instance, I already have 10 volts here. And if I want to know like how much voltage I have on this component here and this component here, then we can go right here on the menu option and we can click on draw. So I'm gonna click on draw. I'm just showing you this first hand so you can have this tool available and you can use it as we go through all these different circuits. That way, if you see, let's say, a combination circuits that seems complicated and you are not sure how is the current flowing, this will give you like a clear picture right on the screen that will tell you how is the current flowing, what is the amount of current that you have on each individual component, and how much is the voltage that you have as well. So as you can see, I click on draw, and I'm gonna go to outputs and labels, and I'm gonna move to where it says voltmeter. When I click there, what I'm gonna be able to see is just like a little line that have like a voltage in between, like a voltage measurement that is gonna have in between. But right now you can see that it reached 0. So in order to connect this voltmeter, I have to be able to identify the connection point. I'm gonna show you that as well, okay? So if I hover, okay, I'm gonna stop the simulation. So if I hover over here, over that wire, you can see that a little connecting point right here has been highlighted, okay? So I will be connecting my voltmeter between that point here and this other point in here. So now I will go back to draw and I'm going to add a wire. So from there, I'm just gonna click. Okay, I'm gonna do like a left click, hold it, and just go to the spot where I have my joint, my connecting point. So now I'm gonna rerun the simulation. Let me run it again. So when I rerun the simulation, you can see that here, we actually have like minus, okay, like minus 909 millivolts, okay? And you are gonna say, well, but I don't wanna see this as a minus. And the reason why we had a minus is because the voltmeter indicates that we have reverse polarity, that we are measuring this with the meter in reverse. That being the case, all we have to do is just do, okay, let me get back. So I'm gonna press escape so I can get back on my cursor so I can see my cursor again. I'm gonna do that once more. Like if I were here on adding anything, whenever you are adding a component, you are going to see that little cross. But if I wanna go back to my cursor so I can select an individual component, I'm just going to press escape. Now that I press escape, I'm going to hover over the component that I want to change. And there's two different ways that you can do this, okay? Like in my case, I'm going to do this. I'm just going to do a right click, and then I'm going to go down pretty much on my list of on my menu option, and I'm going to click on swap terminals. When I do that, you can see that my voltage now is positive because now my voltmeter is connected in the right polarity. If I want to measure this voltage down here, you can see it as well. Well, I'm using my cursor, that as soon as I go down into this other resistor, then the connecting point are highlighted right away, okay? So I'm going to stop the simulation. Okay, so our connection points are being highlighted here, like the two squares at the bottom, like right here and right here. So what I'm going to do in this case is I'm going to go back to my meter. I'm going to do a right click. I'm going to copy. And I'm just going to click here and then say, well, that didn't work. That didn't go as expected. I'm going to, instead of copy, sorry, let's just say duplicate. If I duplicate, then I'm going to be able to see a second meter that appears. So I'm just going to take my meter and I'm just going to drag it down as I did here. And we can do this. I always like to add wires because it looks better. So let's add the wires as well. That's the connection point. And that's the other connection point. Like if I were going to connect it, let's say like right here, okay, like this one. If I were going to connect it in one spot where I don't have a connection point, okay, you can see that it's going to give you like a red dot indicating that that point is not connected. And when you run the simulation, okay, oh, I'm surprised, it's reading it. Usually it doesn't read it. Maybe they updated the software. But I'm just going to swap the terminals so I can see this as a positive voltage. So now you can see that my 2 voltmeters can read how much voltage drop we have on each individual component. So let's keep moving then. Any questions so far?
No.
No questions. We're good. Okay, so let's get into the, that was just to give you the heads up. So now we are going to be getting into our lesson today, which is series circuits. Let's begin. One of the important things that we are going to discuss when it comes to series circuits will be, number one, we are going to be discussing the properties of a series circuit. We are going to be listing the 3 rules, and they are very important to keep in mind. Okay, guys? So today we are going to discuss like the 3 rules for series circuits, and I'm going to give you a little bit of time so you can play a little bit with series circuits, and then we are going to jump into parallel circuits. I have to teach you both circuits today, okay? And then you are going to have the rest of the week to go through the material slowly, so you can have a good grasp of both series and parallel circuits before we step into combination circuits. And then we are going to be able to calculate values of voltage, and we already did that using Ohm's law, and we are going to be using Ohm's law extensively, combined with the 3 rules, okay? And the 3 rules, they are for voltage, for current, and resistance. And I'm going to tell something from the very beginning. When it comes to power that we are going to be calculating as well, yes, indeed, we know the formula that we are going to use for the power, but I'm going to say this from the very, very beginning, and I'm going to repeat it throughout the course. I mean, throughout all these other lessons that we are going to have. We know that power is equal to E times I, and that's very important. Well, because we know that the product of voltage and current is going to give us the amount of power that we are using in any given component. Now, when it comes to determining power in a series circuit, we are going to call this PT, total power, and I'm just going to use two components. Let's say that we have power on resistor 1, plus we are going to have the power on resistor 2. Well, let me put another resistor here for convenience. Power on resistor 3. So if we had 3 resistors, each one of them are going to exhibit or are going to have some power dissipation. So the total power that we are going to have in the circuit, in any given circuit, is going to be equal to the sum of P1 plus P2 plus P3, regardless of the way in which the resistors are connected. It doesn't matter if they are connected in series, okay? Like if this was the little wire that is connecting them, that's going to be a series connection. Let's say that here we have the positive terminal and here we have the negative terminal. Then that resistor is connected in series, and that's going to be the formula for power, okay? Power adds up. If these resistors were connected, let's say, in parallel, and that's how parallel looks, in which they have a common point that they share on both the positive and the negative. Okay, that's parallel. And then if this is the positive and this is the negative, P1, P2, and P3, power it still adds up. So I just saw a message here that the presentation link is not working for someone. Rob?
Yeah, it's not coming up on my screen. It says,
Yeah, not working for me either.
So just go, I always have 2 different screens, and the one that I'm using right now is the main screen. But just try to go to your, let me see how I can show you this.
Yours is working. Like we can see yours, but online on your desire to learn, we can't open up the presentation ourselves.
Okay, because you would like to be able to open the presentation so you can follow along?
Yeah.
Okay. I'm going to take a look at that pretty quickly. Okay, and then let me just
Thanks.
finish this thought, and then I'm going to check that.
Yeah, thank you.
You're welcome. So what I was going to tell you guys, so in this instance here, we have a parallel circuit, and still the formula for total power, it will still be this one, okay? Now, if I were going to do something like a combination circuit, and a combination circuit is not more that I take another piece of wire, and then I connect the 3 resistors that I have in here, I connect it with the 3 resistors that I have in here in parallel. Now we have a combination circuit. Now we have a series parallel circuit. And that being the case, okay, so still we have an input and an output, and all this are going to be in series, and these 3 are connected in parallel. And if I were going to determine the power, yes, indeed, of course, now we have 6 components, and now I gotta add like P4 plus P5 plus P6. And indeed, the formula still remains the same. Still, the total power is gonna be equal to the sum of all the components that are using power throughout the circuit. Okay, so the last thing that I was telling you was that the three rules that we are going to be discussing apply to voltage, current, and resistance, and that power is always the same regardless on the way or regardless in which way the resistors are connected to form a circuit, okay? And also we are going to be using another formula today, which is called the voltage divided formula, in order to calculate the given value of the voltage drop in any resistors around a closed loop. So the three major types of circuits are series, parallel, and combination. Like in our case, in level 1, we are going to see series, parallel, and combination circuits using resistors. When you advance to level 2, and that's why I made so much emphasis on why it is so important to be able to do these circuits, because, okay, like here, we have just two resistors, let's say connected in series, or we can have two resistors which are connected in parallel, okay? They have common point of connections, as you can see in here, or we can have a combination circuit. Now, in our level, in level 1, we are going to use resistors only for this type of circuits. When you advance to level 2, then you are going to be using series circuits, but now you are going to put another components like inductors and also capacitors. And you are going to be using trigonometry in order to solve for current, power, and you are going to get into other themes which are called power factor, efficiency, things like that, okay? So it's supremely important that we feel very, very comfortable with this before you can add these other components, which is like inductors and capacitors, okay? So let's keep moving. So in a series circuit, we only have one path for the flow of current. As you were seeing in the simulation site that I showed you this morning, the little yellow dots only have one flow. They only have one path to flow in order to go from the output back into the source, okay? And that is the characteristic of a series circuit. And you may wonder, okay, so when in the field will I ever use a series circuit? Guess what, guys? We are using them all the time. Even when they are not resistors, like in our case as electricians, every single thing that we are connecting in the field is connected to something like this, a circuit breaker. Or any single switch that we install for a light, guess what? It is also a series circuit, okay? So like if we have a light here, that light, even when all these lights are gonna be connected in parallel in between them, at the end of the day, they are controlled by a switch. And the switch is connected in series with all these lights. And the breaker that is protecting the wires that are connected to the switch and to the lights is connected also in series with the whole circuit, always. It cannot be any other way. Why? Because what we want to happen is that we want each individual, we want like all the current to flow through the oval current device before it reaches its target. Okay, so this is what I was telling you just now. In this instance, we have a DC motor. And of course, we are gonna have a fuse. And it doesn't really matter if it's like a time delay fuse, okay, or if that is a breaker, it doesn't matter what it is. The overcurrent device is always connected in series with the load. Because that way, if we have an excess amount of current or we have an overload, our OCD, our overcurrent device, will trip and stop the insulation from the wires from getting damaged. Okay, so let's get into the first rule for series circuits. The first rule reads that the sum of all voltage drops, and voltage drops means the amount of voltage which is required to push the electrons through the component, through the resistor. So the sum of all the voltage drop across all the resistors must be equal to the applied voltage. Okay, so there is another way to say this as well, which is called Kirchhoff voltage law. Kirchhoff voltage law says that the algebraic sum of all the voltage around a closed loop will always be equal to 0, which means, in other words, that if we have, let's say, if we have 20 volts here, and that's my input voltage, and let's say that all these resistors are equal, okay? So I'm gonna ask you that question, from this statement on the top, then I'm gonna tell you that all these 4 resistors are of equal value or has an equal value. So if the sum, okay, of the voltage across these components has to be equal to the applied voltage, then how much is gonna be the voltage on each component? If
5.
all of them, 5 volts, perfect. It cannot be any other way. Okay, why? Because we cannot create energy. So if all these guys are equal, then all of them are gonna have 5 volts. Now, let me ask you one more question. What do you think is gonna happen if, okay, so if all of them are equal, I'm not gonna give any values to this. It's just that you have an idea. Let's say that this one is equal to this one, and I'm gonna use the blue. I'm gonna say that, okay, I'm gonna use this green, whatever. Oh, well, I thought it was going to be a, oh, this doesn't want to change color. Okay, I'm gonna use this color, this orange. And I'm going to say that this, and these 3 are equal. They have the same value, but my last one, this one here, it's twice the value. Okay, like it has like a higher value than the other 3. So in that instance, I still have my 20 volt input, but my question is, which one do you think is gonna have the higher voltage? Like if this is have a high resistance, okay, I'm gonna give you numbers because it's gonna be easier if I give you numbers, okay? I'm gonna say that this one is 3 ohms. I'm gonna say that this one here is 2 ohms. And I'm gonna say that this one here is 5 ohms. But I'm gonna say that this one, the one that I want to say that is high, is 10 ohms. And I want you to look at the following. Like in this instance, we have a series circuit. And yes, I'm gonna jump, and you are going to see one slide later. I'm gonna jump into the next rule, that the sum of all the resistors, of all the resistive values around the closed loop is going to be equal to the total resistance. So in this case, I have 3 plus 2 ohms is equal to 5 ohms, plus 5 ohms is 10 ohms, plus 10 is equal to 20 ohms. So the total R value, RT, in this circuit is going to be equal also to 20 ohms. I did that on purpose because I want to be able to use Ohm's law, and I want to be able to get only 1 amp, just to make things easier to see. So I is going to be equal to E divided by R. So we know that E is 20 divided by R, which is 20. That's going to be equal to 1 amp. Now that we know that we have 1 amp throughout the circuit, we are going to be arriving to the third rule. In any given series circuit, current is going to be the same at each individual point. Because if we have 1 amp getting out of here, energy cannot be created nor destroyed. So we are going to have 1 amp returning here. It cannot be more, it cannot be less. Okay? So this 1 amp is going to go through this component, do its work, and it will jump to this component then, do its work, and it will continue to this component, and it's going to be the same 1 amp that is going to go throughout the circuit. So that being said, and going back to the question that I was asking you, where are we going to have the max voltage drop? Well, if we use Ohm's law, now I can see that I can find E, and in this instance, I'm going to call this E1 because I'm going to consider that this is 1 or R1, this is R2, this is L3, and this is L4, okay? So now I want to know how much is going to be my voltage. So E1 is going to be equal to I times R. So when I do I times R, I'm going to have on this resistor a voltage drop which is equal to, well, I, which is 1 amp, okay, 1 amp, times R, which is 3 ohms. Here we're going to have 3 volts. Here is going to be the same equation, 1 times 2. Here we have 2 volts. Here on this one, we have 5 ohms, 5 times 1, that's going to be 5 volts. And on the last one, then we are going to have 10 volts. Why 10 volts? Why do you think that we have 10 volts right here?
Because R times I equals 10.
That is true, because I times R equal 10. And also we are gonna use them, I mean, like if we are trying to push 1 amp through each individual component, remember the definition for voltage. Voltage is electrical pressure. It is the pressure that is pushing the current through the components, through the resistors. So if we have more ohms here, if we have more opposition here, it's going to require more pressure to push that current. Okay, so naturally, the voltage is going to be splitting up as per the requirement of each individual component. On the spot where you have more resistance, then you are going to have more pressure naturally. Okay, so let's keep moving then. Any questions about this? So I already gave you the 3 rules, but just to brush once more over them. Rule number 1 was that voltage is going to be the same, that the sum of all the voltages around the closed loop is going to be equal to the source voltage. That's rule number 1, okay? And in the case of rule number 2, so in the case of the rule number 2, I'm going to give you that the current is the same at any point in the circuit, and the total resistance is the sum of the individual resistors. So we already covered like those 3 rules. Okay, so please keep those in mind. Those are very important going forward into combination circuits. Do you have any questions so far, guys?
We always use the electron flow theory though, negative to positive when we're figuring this out.
It doesn't make any difference. It doesn't really matter if you use the electron flow theory or if you use the conventional flow theory. So just to illustrate that, let's say that if I assume, in our case, in theory, we are always assuming that current flows from negative to positive, and it flows like this, right? In that direction. Why? Because we say that electrons flow. But you can see that by all means, if I were going to assume the conventional flow theory, and I said that holes are flowing from positive to negative, you then change the circuit a bit. You would still get the same result, same values. It doesn't change at all. So also something else that I want to show you here, guys. If I were going to use like a battery, that's DC, all these values are good, okay? So if I were going to change this by an AC source, and usually when we portray an AC source, we just draw a circle. And in that circle, we add like a frequency, like 60 Hertz, which is the frequency that we use here in Canada. And then if I were going to use the 120 volts that we are using right here, okay, and now I have AC voltage applied to the resistors, none of these values will change. All these values will remain the same. Why? Because they are resistive values. In a pure resistive circuit, it doesn't really matter if you apply DC or AC, the values, the way in which the resistors are going to behave is going to be the same. Any questions about that? Now, the next one, now that we know our 3 rules, then let's give a little bit of a shape to these rules, like the first formula here. Okay, so we can see that RT is going to be equal to R1 plus R2 plus R3. Now, I'm going to tell you something. Let's say that we have a circuit in which we know RT, and let's say that RT is equal to 100 ohms. Just to make things easy, okay? That's going to be my RT value. Okay, and let's say that I don't know how much is R1. I don't have a clue. But I know what is the value of R2, and that one is 30 ohms. And let's say that R3 is equal to 20 ohms. Would you be able to determine the value for R1?
Yeah.
Yeah, so what do you do in that instance?
Subtract.
Pardon?
Subtract.
Perfect. So we are going to transpose the formula, and we are going to say that, well, because I know RT, and I know RT, and I know R2 and R3, all I have to do is to isolate R1, because that is the variable for which I don't know. So R2 and R3 are adding, so both of them are gonna go to the other side of the equals sign, performing the inverse operation. And now you can see why, when we started this course, I was getting you into all this simple math and transposing and small equations. It's because we have to use them a lot in this course, okay? So in this instance, we have that R1, then I'm gonna rewrite the formula, is equal to RT minus R2 minus R3. And when we do that, we are going to have 100 minus 30 minus 20. So R1 is equal to 50 ohms. And you can see that by all means, that the formula stays intact. You know, nothing has changed. Now, the next let me delete all this. Okay, so the next rule that we were discussing is that the total current is equal on each individual component. So if I have a total current, as I was showing you in the little example of 1 amp, that's how much is coming out of my of my battery. So if I had a battery here, this is the symbol for a cell. That's fine. I'm just gonna call this cell a battery. So if I have 1 amp coming out, that 1 amp will go throughout the circuit, and it's going to come back home to the positive terminal intact. I'm gonna have 1 amp back. Now, this 1 amp is gonna be doing its work on all the components, and it doesn't really matter if I have only 1 resistor or if I have 10 resistors. This 1 amp is gonna be the same on each individual component. Okay, so that's why that one of the rules is that the current, it's the same on each individual resistors in a series circuit. Now, and the other rule that we saw was that a voltage is going to be like the total voltage is going to be equal to the sum of all the voltages around the closed loop. I think that at this point in time, we are already raining over wet. Okay. So any questions? Now, one of the important uses also of series circuits is that with a series circuit, we can create what is called a voltage divider. Okay. In this instance, like if I have an input voltage of 200 volts and I want to obtain different step voltages throughout the circuit, I can adjust the resistance in the circuit in order to obtain whichever voltage that I want to obtain. Let's say, but the only thing with voltage dividers is that they only work for very small currents. Like if you were going to use large currents, you are not going to be using a voltage divider. You are going to be using a transformer in that case, like especially an auto transformer. But in this instance, if I only needed to use, let's say, like 5 milliamps from this 20 volt source, 5 milliamps from here is not going to cause, it's not going to wreak havoc. So if I were going to connect something to this 20 volt source, and that something is going to be drawing only 5 milliamps from the circuit, there's going to be like a small fluctuation and a small variation throughout the circuit, but it's not going to be like a prominent variation, okay? So we can use a voltage divider with a small current output. So in this, because once you do this, of course, once I connect another resistor, which is a load, to between point A and B, immediately I am creating a combination circuit, okay? So as long as this resistor doesn't draw a lot of current, I'm not gonna be affecting the rest of the circuit, and I'm gonna be able to enjoy my 20 volts because this other resistor that I was able to connect in parallel between point A and B is not going to be causing like the total value to change dramatically. There's going to be a small fluctuation, but at the end of the day, the circuit is going to remain relatively the same. Okay. So, well, that's one of the uses to use the resistors and connect it as a voltage divider. And the advantage of that is that if you were going to use it for a small currents outputs, then you don't have to use a bulky transformer. A transformer would be way more expensive and way bulkier, while by connecting like a few resistors in series, if you have an input of 200 volts, you can get all these different voltages for a very, very low price because they are rather cheap, okay? Plus, it's gonna be very simple to build as well. So you're seeing a formula here. I'm gonna leave this for you to see it. But what I really wanna take you with this is that in order to determine, there is something which is called the voltage divider formula. In the voltage divider formula, you can determine, and I'm gonna go one slide, 2 slides back, 1 and 2. If I wanted to determine how much voltage do I have on each individual component, in this instance, of course, we are seeing the voltages, but let's say that instead of voltages, we have resistors. So I'm gonna give you another circuit, okay? I'm gonna give you a sample circuit. Let's say that we have the following. Okay, so we have a power source, 1, 2, and 3 resistors. So according to this formula, which is the voltage divider formula, it says that X is what? The value that I want to find. So this one we are gonna call R1, this one is R2, and this one is R3. And of course here, okay, right at the source, when I measure with an ohm meter, if I wanna be able to determine my RT, I'm gonna have to measure between these 2 points, between here and here. Let's call these 2 points A and B. So if I want to measure my total ohms, it's going to be measured between A and B. And because it's going to be measured between A and B, right here also between those 2 points, we find RT. So right at the power source, I always write down RT, ET, IT, and then of course, PT, which is on total power. Now, going back to this formula, if I have, let's give some random values to this. Let's say that R1 is equal to 10 ohms. Let's say that R2 is equal to 20 ohms. And let's say that all three, I just want to keep things very simple, okay, is equal to 30 ohms. So I'm going to say that my power source is equal to 120 volts. That means that when I use Ohm's law, we can do this 2 different ways. Off the top of my mind, I would be able to say, well, 120 divided by 60 is going to be 2 amps. Okay, but because what I want to do here is just to show you how to get this voltage here, which is E1, without having to do any other calculations. Well, what we are going to do is that we are going to say that, well, I want to find E1, and I'm going to substitute all these different values in this formula. So I'm going to say that E1 is equal to Rx, which, what is Rx? 10 ohms. Divided by RT. So we already know the value of RT to be 60 ohms. And then we are going to multiply that by ET, which is 120 volts, which is a value that we already know. So when we do that, what we are doing in reality is getting like, what is the percentage of the total voltage that this individual component is taking? And by determining the percentage that each individual component is taking and multiplying that percentage into 120, then we are going to be able to determine how much they are getting, what is the share, okay? So if you do me a favor, please, can you, perform this operation?
20.
So, perfect. So E1 is going to be equal to 20 volts. And simply enough, that's just how you use the voltage divider formula. Any questions about that formula? Questions or comments? Any doubts?
Is there a reason why they're using E instead of V for voltage?
Yeah. The only reason why, like mostly we use E. Like in my case, I like to use E instead of B. Some teachers like to use B. It's just because it's just to avoid that redundancy. Okay, it's because E means EMF. That's what E means.
Oh, okay.
Electromotive force. Okay, and also you can say that you have electromotive force or that you have voltage. So when you say like, okay, V is equal to 120 V, it's kind of redundant. So sometimes I think it's more convenient just to say that my electromotive force is equal to 120 volts.
Yep, gotcha.
And that way we avoid that redundancy.
Yep.
Okay, perfect. So anyways, guys, what I'm going to do is that I'm going to give you like your 10 minutes break. And then I'm going to put like 10 minutes on the screen. I'm going to be logging into my other computer where I can have a little bit more quietness. But I'm going to give you your 10 minutes break. And after the break, okay, something that I want you to be able to do, and you can start doing it now if you will, okay? But it would be nice if you rest for a few minutes. But what we should do next is that I want to give you a little bit of time in order to get into doing some of these circuits. Okay, so I want you to be able to Get into here what it says, like number 2, series circuits practice questions. So I want you to go into these practice questions and play with it. Okay, so either if you decide to do it now, or if you decide to do it like after we come from the break, I'm gonna be totally okay with it. And then we are gonna spend the next half hour after the little break going over this page. Okay, so we are gonna go over this page, and also we're gonna go over, okay, let me see if this is the one, this other page here. Okay, so this is how you'll know if you really understand how a series circuit behaves. Like if you can solve this, you can count on the fact that you really know, that you really have a good understanding on how a series circuit behaves. So, well, anyways, beginning now, I'm just gonna put the timer, 10 minutes. Go for a break. See you soon. So as I was telling you before the break, I want you to be able to, give a try to a couple of these questions. So please make sure that under the weekly lesson, you open this document, which is called number 2. And let's just begin with something rather simple, okay? So which is the very, very first question. So if you didn't have a chance to do it while you were on the break, and I didn't expect you to do it while on the break, then please go ahead and take a couple of minutes and get it done. And if you have any questions about it, then please let me know. So can you hear me well, or can you see my screen? Can you hear me well? I just came.
Yes.
Perfect. I can hear you well as well. Thank you. So it's just that I have 2 different computers. So I build the computer that I'm using right now. I build it just for this, okay? It is a powerhouse, but I cannot use it. It's in my bedroom, and I cannot use it before my children wake up, because otherwise it was a little noisy. It was getting a little noisy downstairs. They are excited to go back to school today. So are you okay then with doing this little problem here? Okay, so are you done so far with this first one? Or are you still working through it?
Done.
I'm done.
Done.
Okay, so like when you know that at any given point in time, like if you want to verify if the answers are right, all you have to do is just to go to the answer key. So if you go to the answer key, okay, gonna go back here. So you can see like what the answer was for that circuit, okay? Can you see the answer key there?
Yep.
Perfect. I usually use 2 screens. To separate accounts to be able to see what you see, but my telephone is upgrading or whatever, like it is on an upgrade of Zoom. So I'm gonna have to wait to be able to see my second screen. Okay, guys, so, well, that being said, so let me give you one more thing here, okay? So I want to show you that something that you are going to encounter in the case of series circuits. Let me get back to the questions. Okay, I know that you will not encounter any issues up to this point. Like all these circuits are very straightforward. It's just the same thing repeated over and over. However, when you get to something like this, can you see the circuit number 5?
Yeah.
Yep.
Okay, so give me just 1 minute so I can go back into connecting my other account.
Put my headphones in.
But do you want to ask a question? Okay, perfect. I got my second account now. I'm back in online. Okay, perfect. So what I was going to tell you now, guys, is that in this instance right here, you can see that we have like how many power sources? We have 1, 2, and 3 power supplies. That being the case, you may wonder, so how do we go about solving something like this? In order to solve something like this, we gotta get into the idea of additive and subtractive polarity. So let me show you something, okay? So I'm gonna be turning on my camera. Okay, you should be able to see me now, even when I am using my second account, or maybe you don't see me at all.
Yeah, we can see you.
Okay, you can see me. So, okay, now that you can see me, I'm going to show you something, okay? Like if you have a battery like this.
Yeah, I can't see. It just shows your name for me.
Oh, okay, so you have to go into, on Iconestoga, excuse me, on the Zoom control, right on your right-hand side, you have like 3 little tabs, and one have like a bunch of little squares. Do you see that one?
I got the chat on the right.
It just shows that your camera's not on.
Yeah, that's what it looks like to me. I just see your name in the black box.
Yeah, I'm using another camera, but that's okay. I'm not what I'm going to do, I'm just going to show you like without that camera. I know that some of you can see me, some of you cannot see me. It's like if I were, because I'm using my second camera, it's like if I were a student. But this is what I wanted to show you then, okay? So let's say that here, just concentrate on the screen itself. We have the following. We have one battery here, okay? So when we have this battery right there, we have a negative and a positive terminal. If we have another battery here, and this is negative and positive as well. Okay, so let's say that this first battery have a voltage output of 5 volts, and the second one have a voltage output of 10 volts. When I connect a piece of wire between them, I'm going to use this red wire and make a connection between them. And anything that I connect between these 2 points, that point and this point in here, because I connected the batteries negative to positive, and they all connected in series, that is a series circuit, negative to positive or positive to negative, whichever way you want to call this. Now we have what is called additive polarity. And when we have additive polarity, we are going to have that this voltage is going to be adding up to these volts, and the total output voltage is going to be equal to the sum of the voltages, in this case, 15 volts. Fair enough?
Yeah.
Yep.
Now, guys, now look at what I'm going to do with the same thing. if I were going to use the same battery, I'm gonna delete this wire and this wire. And now I'm gonna take my wire and I'm gonna connect positive to positive. Can you see that? And then as my output, I'm going to have like the two negative terminals. Of course, one of them is gonna be more positive than the other, and then we are gonna have a positive and a negative anyways. But because I connected positive to positive, we accomplish what is called subtractive polarity. So in this case, instead of having 15 volts, we are going to have only 5 volts output. Why? Because we are going to have 10 minus 5, which is going to be equal to 5. Now, when you look at a problem like this, you got to go around the circuit and you have to determine whether we have additive or subtractive polarity. So if you look at this, let's say that we are going to start from this 25 volt power source. So we have that this negative is connected to, so let's follow along the circuit. Negative is connected with negative. So that means that those two batteries are connected in subtractive polarity. Okay, and also if we go on the other side and we just draw a line along the circuit, along the path, we can see that this positive is connected with that positive again. We can see that the power source that I encircle is connected in subtractive polarity. You can see that these two guys are going to be adding up because they all connected negative to positive. So we have 75 plus 50. That's going to be equal to 125 volts. No problems there. So 125 volts minus 25. So the total applied voltage in the circuit is going to be equal to 100 volts. So by all means, you can redraw the circuit now, and you can say, well, I have a 100 volt source with your R1, R2, and R3. Okay, so the circuit is reduced just to having one power source only with 3 outputs, with 3 resistors. Any questions about that? Does that make sense?
Yep.
So the reason why we showed you like the difference between subtractive and additive polarity is because that way you can make sure you never made a mistake of connecting batteries backwards, because if you do, you are not going to get that output voltage. And also it shows you once more, it confirms once more that rule that in a series circuit, voltage always adds up. Okay, so let's get moving then. What I want to do now is that I want to give you a couple minutes to finish solving this circuit, now that you know how to solve it, and get back to me on your findings, please. So I'm just gonna leave like this other one for you, but that's gonna be in your spare time, you know, like after we finish this class. I know you have another class, but please, between today and tomorrow, make sure you go to that circuit over here. Now, something that I want to cover with you is this other circuit, which is called the voltage divider handout. Okay, so, and this is just an analysis. We could do this 2 different ways. Either we draw the circuit using FalStack, and then we apply like different voltmeters to see what happens, or we can just analyze it here. So, and what I'm going to do just to save time is that I'm going to let you build it yourself on FalStack. but I want to be able to cover with you what happens in a circuit like this. In this case, we have that, well, we have a power source being 100 volts. So we got 100 volts for the source, and then we have the following voltage drops across the different points, C, D, E, and F, 60, 30, and 10, which of course, we can see that the rule that the voltage, the sum of all the voltages around the closed loop is going to be equal to the source of voltage. Now, when the switch is open, so when this switch is open here, then what's going to be the value of the voltages around the closed loop? By all means, okay, we can see that if these were light bulbs and we open the switch, by all means, we can say the following. Okay, so we can say, well, when my switch is open, I don't have any doubts that between C and D, I'm going to have, let's begin to see the points here, C and E. C and E, that's going to be 0 volts, because if these were light bulbs and the switch is open, that would be off, right? C and F, that's going to be 0 volts as well, because it's going to be off. D and F, of course, is going to be 0 volts. All that is 0 volts. As soon as we open that switch, we interrupt the flow of current, and then we don't have any voltage because we don't have any current either. Okay, so, and then between D and E is going to be 0 volts as well. Now, the interesting question here, of course, I mean, it doesn't really matter what I do to my switch, AB. My power source is my power source. That, by all means, is 100 volts. Okay, so what's going to be the voltage drop? Like if I were to take a meter and measure between these 2 points, between A and B, with my voltmeter, my red and black lead, my voltmeter is connected between point A and B. So how much voltage do I have?
100.
100 volts. Perfect. You know why?
Potential difference.
Yes, perfect. Always right at the switch, we always have the full voltage. If we didn't have this voltage here, then when we close the switch, nothing is going to work. Okay, so you can see that point A is connected straight to point H. So that's going to be our positive terminal by all means. And through the circuit, we have this other point, the negative terminal connected to point B through the circuit. As long as these resistors are good, as long as they are not open, we are going to measure 100 volts right here between these 2 points. Fair enough? And as I said, this is something that you can do on FalStat just to verify the information. You can simulate it, or you can download Multisim, which is completely free to you guys until June of this year. And you can also do the same simulation. If you need help downloading Multisim, I can show you later today where to go in the college, where to go on the IT website in order to download it. But I always go to FalStat because you don't have to download anything. And for the course that we are doing, is good enough. Okay, so now when we close the switch, now that the switch is closed, indeed, if these were light bulbs, all the light bulbs are going to be on, and the power source is not going to change. That's still going to be 100 volts. Now, between like all this I'm gonna leave the switch for the end. Between C and E, how much voltage we have? C and E, it's gonna be this plus this, right? 60 plus 30. That's gonna be 90 volts. Between C and F, it's gonna be 100 volts. And this is just repeating like that idea that voltage add up in a series circuit, okay? D and F, that's gonna be your 40 volts. And then when we get to here, DF, oh, DE, sorry, DE, that's gonna be 30 volts. Now, the question would be, how much voltage do we have between A and B?
0.
0 volts, perfect. Do you know why we have 0 volts, guys?
Because there's no difference.
Yeah, but why don't we need any potential difference across the switch? Well, if you think about it, when we have an open switch, if we have an open switch and I want to measure the ohms on my open switch, how many ohms will I get on my open switch? Pretty much.
Open line.
Yeah, perfect. It's gonna be infinite ohms. Having infinite ohms, that switch will have full voltage drop. And if I have a closed switch and I measure with a meter, how many ohms do I have across a closed switch?
Next to nothing.
Next to nothing, 0 ohms. So what is the potential difference that is required to push current through a 0 ohm component? Nothing. It's pretty much a dead short. With a minimum amount of voltage, current will go through. Kind of make sense? The last portion of it, okay, which is the last portion of this question, which is right at the end. I'm gonna leave it completely up to you. Because if I do it, what's the point, right? So that one, I'm gonna leave to you. Now it's asking if resistor R1 were to burn out an open circuit between C and D, and you have an open circuit between C and D, what are the following voltages? So I'm gonna leave that up to you, and if you have any questions, once you compare that to the answer key, then please get back to me. Okay. So now, are you ready to start parallel circuits? Okay, guys, so now that we are onto parallel circuits, let's get into parallel. Now, how do we know when a circuit is connected in parallel? That's what we started with this morning. And number one, it doesn't really matter how a circuit looks. What really matters is how the connecting points are interconnected between them. I'm gonna make myself clear about this. Like this morning, I showed you that if we have 2 resistors and they are connected, each one having a common point like this, okay, where I have R1 and R2, and then I have what is called a node. That's called a node, or a point of connection. So if this is 1 and 2, because they are connected, number 1 and number 2, resistor 1 and resistor 2 have a common point, which is called a node, connected in common to the positive terminal, and connected in common to the negative terminal, they are considered to be connected in parallel. And not only considered, they are connected in parallel. So that's the standard look of a parallel circuit. However, if I were going to draw one resistor here, another resistor here, another one around here, excuse me, another one around here, and I have now 3 resistors, 3 random resistors. If I ask you to connect them in parallel, well, let's say that we are going to use red for the positive. If I do this, and I connect 1 point from each resistor with the same wire, and I take my second wire, and I connect the other point of each individual resistor to the black wire. Now you can see that the 3 resistors share a black wire in common and share a red wire in common. That is a parallel circuit, even when it looks completely different than the one that we have right here on the top. Okay. And that's the idea that I want to be able to freeze in your mind, that when we have a parallel circuit, we only have 2 wires. Okay, only 2 wires pretty much, one red and one black. And it have all the resistors connected in common to that red and to that black. Okay. Now, so in the next PowerPoint, we're going to be discussing like the 3 rules for solving the values of parallel circuits. And it still is going to be the same 3 rules for voltage, current, and resistance. Now, when it comes to resistance, we are going to be using like a few different formulas in order to determine RT, the total resistance for parallel circuit. So let's keep moving. So there's something that I don't want to get into right now, okay, which is the current divided formula. And the reason why I don't like getting too much into the current divided formula, I will show it to you, but I'm not going to be giving you a lot of problems with the current divided formula, because if we have Ohm's law, and also with the voltage divided formula, if we have Ohm's law, we don't really use them very much, okay? So then let's get into this. So all the lights that we have in our houses, all the lights in the house, all the receptacles in the house, all of them are connected in parallel, all of them. Why? Because one of the big features is that in a parallel circuit, voltage stays the same, okay? So that's one of the big rules for parallel circuits. The voltage drop across any branch is equal to the source of voltage. So remember the circuit that I was doing with a lot of weird, resistors in a lot of weird positions like this? Okay, so I'm gonna make another one like that. And then we are gonna connect them in parallel, and we are gonna connect them to a power source. So here I'm going to have my, okay, so I'm gonna have my positive terminal. And just for the sake of to make things easier, here I have my negative terminal. And now what I'm going to do is that I'm gonna be using my red wire, and I'm gonna connect 1 point of each individual resistor in common. So just to make life easier, I'm gonna go to there. You can see that all the resistors have 1 common red wire. Now I'm gonna do the same thing with the black. Okay, so if my power source, it's equal, let's say, to 10 volts. When you take a voltmeter and you measure the voltage across R1, you are going to have 10 volts. And it doesn't really matter if you go to R2, still you have the same 10 volts. On R3, you are going to have 10 volts, and on R4, still you are going to have the same voltage, 10 volts. And that's one of the most important features and characteristics of a parallel circuit. Voltage remains the same at each individual point. That's why it is used to connect all the receptacles and all the lights in a house. Everywhere, in industry, anywhere you go. You always want to have the same voltage. Okay, so the other rule for parallel circuit is that the total current, okay, so let me give you another example. Let's use this blue color, full current. And I'm gonna do this. I'm gonna say that my current is flowing from negative to positive. So if this is my amps, so right here, you can see that all the current that is gonna flow through the resistors is getting out of the negative terminal. That's why I had a big circle, okay? So now each individual component, okay, is gonna take, this is gonna take some amps, but this resistor is completely independent from this other resistor here. So this is gonna be taking its own amps, and this is gonna be taking its own amps, and this one is gonna be taking its own amps. So each individual branch is getting the same potential difference, my 10 volts, and each one of them is drawing its own individual current. But because everything is coming from the power source, then we have that the total current flow, that current flow, is equal to the sum of the currents through all the branches. Okay, so if we were going to have, let's say, like on this one, I'm just going to give numbers because I haven't given you any resistor values. I can give you any arbitrary numbers in this instance. I'm going to say that here we have 2 amps. And here, I'm going to tell you that we have, okay, let's do something fun here. Let's say the following. Let's say that according to the numbers, that we have the same amount of amperage. Oh, that one. That's okay. So let's say that on this one, we have actually 1 amp. And on this one, we have 2 amps. And on this one, 3 amps. And on this one, 4 amps. Let's say that, okay? So that means that the amount of the value of this little circle here, the total current, which is coming off the power source, is going to be equal to 4 plus 3, 7, plus 2, 9, plus 1, 10. It's going to be equal to 10 amps. Okay? So that being said, that means that if I disconnect, let's say R1 that have 1 amp, now my total current is going to drop to 9 amps. If I connect it back, then I'm going to have again my 10 amps. Any questions about that? Is that crystal clear?
Yes.
Okay, so the most interesting component comes into effect when we get into the total resistance. Okay, so it is important to know that the total resistance is always less. That's a very important statement. Total resistance is always less than the resistance of the lowest value resistors or branch. That's an important thing to know. Okay. And now, like if we are going to illustrate this in the very circuit that we have in here, okay, let's give values to all these resistors now, okay, using Ohm's law. So I want to find my R. R is equal to what? E divided by I? That's what it is?
Yeah.
Perfect. So, okay, so let's do a little bit of math. Okay, so I want you please to tell me how many ohms we have on each individual resistor. So let's begin. How many ohms here on the number 4? It's going to be 10 volts divided by my 4 amps. How many ohms is that?
2.5.
Thank you. 2.5 ohms. That's Ohm's law, right? Only. Now we have 10 divided by 3.
3.3.
Okay, 3.3 ohms. What about this one?
5.
5 ohms. And this one, of course, you know, like if I needed a calculator to do this one, I would be in trouble. Okay, so now you can see that we have the 10 ohms, 5 ohms, 3.3 ohms, and 2.5 ohms, right? If we determine how much is RT, RT though is equal to, using the same formula, to ET divided by IT, okay? So that means that is equal to 1 ohm. Fair enough? So let's see if these rules apply. The total resistance, 1 ohm, is always less than the resistance of the lowest value resistors or branch. The lowest value resistor is this one. Right?
Yeah.
And even when that is the lowest value resistor, it's still, I mean, the total resistance is still lower than that value, than the 2.5 ohms. And you may wonder why. Simple enough. The reason to that is Ohm's law. When, okay, like in Ohm's law, you got to keep in mind that when your resistance goes down and the voltage remains the same, okay, then what's going to happen to your current? Your current is going to go up. So I told you before that we decided to shut down number 1. So if we shut down number 1 completely, how many amps do I have now? 9, right? So that means that when I shut down my 10 ohm resistor, now I have what? Less amps. So that means that if I have less amps, okay, that means that my resistance went up because I didn't change my voltage. When this goes up, my resistance, my current goes down. However, when I reconnect this one, which is R1, my current goes back to 10 amps. Why my current goes up? because my total resistance went down. So every time that we open a new branch, every time we open a new path for the flow of current, the reciprocal total resistance in the circuit will take a dive, will go down. So that is important to keep in mind. And now, in order to calculate this total resistance, we are going to be using some formulas. Okay, so if we have a parallel circuit, and this is the standard traditional shape of a parallel circuit, then you can see that the three rules apply. Voltage, the same. The sum of the currents add up to the total current. 4 plus 12 equal to 16 plus 8, 24. That applies as well. And we can see that by all means that the total resistance, RT, is going to be lower than the lowest of the resistor, in this case, R2, which is 10 ohms. Now, the next thing that I want to get into is how do we get this resistance value? So we have two different ways. What I want to do, I want to show you my calculator from my computer. And the first way that I'm going to show you is going to be the, well, I'm just going to leave my calculator there. So please keep your calculator at hand, because we are going to be using today this letter key here. You might have it as 1 divided by x, or you might have it as, you might have it like this, like 1 to the minus, excuse me, x to the minus 1, no, 1 to the minus x. You might have it like this, like x to the minus 1, like this. And that is a function that allows you to get the reciprocal value. So remember that before I was showing you a circuit. So we're going to use this to solve that circuit. I'm going to show you with the calculator first, and then I'm going to show you all these formulas. So do you remember again, like these values? Please keep in mind these values. R1 is 1, 5, 15, 10, and 30. 15, 10, and 30. So when we go to the calculator, so how do we input those values to find RT? So we have that R1 is 15, so we are just going to type 15. And then we're going to press that key, which is the reciprocal. Then we are going to click plus, and you see how it displays on the top that we have a first value, reciprocal of 15 ohms plus 10 ohms. Press that key again, plus my 30 ohms, and press that key again. Now I'm going to press the equal sign, and that's going to be equal to 0.2. So in order to obtain the real value of RT, I'm going to go back to that key and press that key again. And when I do that, I get my 5 ohms. Okay, so you see that the 5 ohms on the calculator is exactly the 5 ohms that we have for RT on this circuit. Now, any questions? Okay. There are, like, when it comes to determining like the total voltage, like the RT, the total resistance, then we are going to get into 3 different formulas. Okay. So the first formula that we are going to be getting into is resistors of equal value. If we have, let's say, a circuit like this, where we have 3 30-ohm resistors, in order to find my RT when I have resistors of equal value, I'm going to use this formula that says that RT is equal to R. This R is any of the resistors in the circuit divided by N. That means the number of resistors of equal value that I have in the circuit. In this case, it's going to be 30 ohms, which is the value of 1R, divided by 3, which is the number of resistors that I have in the circuit. So that would be equal to my 10 ohms. But we can only use this formula when we have resistors of equal value. We cannot use it for anything else. Now, the other formula that we can use is when we have 2 resistors and 2 resistors only, and they have different values. Like in this case, you can see another circuit here where we have 30 and 15 ohms. In that case, we're going to be using product over the sum, which means that we are going to multiply. We are going to get the product of 30 times 15, 30 times 15, and we are going to divide that product over the sum of 30 plus 15. In other words, we have 450 divided by 45, which is going to give us on our T. Okay, so that RT is going to be equal to 10 ohms as well here.
And that's only in 2 resistor systems, so it's
Perfect.
so it's
That's-
it's just a rule. It's not really useful math at all.
It's useful math in the sense that, I mean, when you have 2 resistors, you can apply that formula to quickly calculate the RT. It's just different ways to do the same calculation, okay? However, when we have more than 2 resistors, we can use the reciprocal formula. If they are of different values, and they are more than 2, like in this instance here, we have 3 resistors, then we are going to use the reciprocal formula, which is the formula that I showed you before coming to this slide, okay? So let's say that we have indeed the following resistors. Let's say that we have 3 resistors, and the first one is 30 ohms. Okay, and let's say that the second one, and we already did this, okay? But I'm just gonna show you once more, 15 ohms, and the third one is 10 ohms. Those are the 3 resistors that I have. Because this is, in this formula, the reciprocal formula, we gotta get first the reciprocal of this value, and it's gonna be reciprocal of the reciprocal. So to show you once more, when we get into the calculator, the way that we are going to input these values will be, okay, so we had, I said it was 30, okay, and then we go to the reciprocal here, plus 15. We click on the reciprocal key here again, plus 10, and we click on that key again. And that's going to be equal. You can see that we have the 30 here, plus 15 here, plus our 10 here. That's going to be equal to 0.2. But because it's the reciprocal of the reciprocal, what I mean by that is, if I take you back into here, into this page, that 0.2 is the product of performing this operation here. When you perform all this operation, that's what you are getting your 0.2. Okay, so now we still have this 1 here. So it's going to be 1 divided by 0.2. That's why you are going to take the resultant 0.2 that you have, and you are going to click that magic key again, and you are going to press the equal signs again. Oh, sorry, I didn't have to do that once more. My calculator just did it automatically, and most calculator will do it automatically. Okay. Any questions about that? Any questions, or we are good? We are good to keep going?
Good.
Now, something I want to give you this little challenge. Well, okay, you already saw this, like resistors of equal value. Something that you can do, like when you have, when you use the product over the sum, I could use for 3 resistors the product over the sum by determining the value of 2 resistors and reducing the circuit to a 2 resistor circuit only. If I take R2 and R3, I'm gonna get 20 for that equivalent resistance. And then now that I have R1, which is connected in parallel, of course, with the equivalent, which is equal to 20, now I know those 2 values only. So by all means, that's gonna be like 20 because both of them are equal. It's gonna be 20 divided by 2, and that's gonna give us the 10 ohms that we have in there.
So if I had like a 10 resistor system, I could do the product over sum rule for the last 2 and then just keep on adding 1 more. I mean, it's not really a way to do it, but you could do that.
Oh yeah, you
could.
Adding. Oh yeah, sure, you could. Sure, it's gonna be a waste of time.
Yeah.
And you were gonna hate yourself after that, but
if it was 3 or 4, it might not be the craziest thing to do if the math was weird or something.
Yeah, you would be. I mean, you could do it that way if you want. But once you get used to using the calculator, in order to determine in order to use the reciprocal formula, it's going to be very smooth. It's going to be very, very easy to solve. Okay, so let me give you a little, like now that you have a circuit on the board, I want to give you like a minute to find well, that's already, RT was already there, sorry. Let's do the opposite. I'm just going to get back to Econestoga. Okay, so under Econestoga, we have like, even when I say Thursday parallel circuits, I would recommend you like that you, actually I'm gonna change it to Wednesday. So it's just to give you an idea that by Wednesday, you should be able to be there on parallel circuits, you know, like solving like all these handouts called parallel. So here we have a few parallel circuits. So what I want you to do, I want you to take problem 1, 2, and 3 and solve those 3 problems. I'll give you a couple minutes. If you need to take a little break before that, go ahead, take like a... Okay, so we can do this 2 different ways. Either I give you a 5 minutes break or I give you the free time now, so you can start getting into all these different circuits. So what would you rather do?
Whatever you want.
Oh, no. Like, I'm just here to help you. So whatever is going to help you the most. How do you feel you are going to be better served? By giving you the time so you can go through these circuits, or by, like, talking more about circuits? Okay, let me show you this one here, for example. It's just that I want you first to get the gist of being able to spend some time working with them before I get you into something like this, okay? Here, still, we have like a dual power source. And by all means, I don't wanna confuse you at all, okay? So here we had a small power source where we have a common connection here. Okay, that's just a node, a common connection. And then we have 120 and 120. This is the same way that our household electrical panel behave, okay? We have 2 phases, phase 1 or line 1 and line 2. And when line 1, even when we are using AC, is negative, line 2 is positive. And you may wonder, wait a second, in the house we have AC, not DC. Well, actually, that is totally right. But you got to keep in mind that we always have, in any given line, a positive, anything which is above this line that I has drawn here, which is the neutral plane. Anything above the neutral plane is positive, and anything below the neutral plane is negative. So even when you have AC, you always have that positive voltage and negative voltage. And the reason why you have conduction between line 1 and 2 is because when line 1, and I'm going to use the red to represent line 1, and I'm going to use my black marker to represent line 2. When line 1 is positive, line 2 at the very same moment is negative. So that's why you have a flow of current between the 2 lines. If they were in phase, meaning if they were both positive or negative at the same time, okay, like if line 2 was here at the same time that line 1 is there, then there wouldn't be a difference in potential between line 1 and line 2. Not any flow would happen because they have the same potential in that case. So in a circuit like this, I just want you to keep in mind that between like this point A and C, we have, by all means, 120 volts. Between point B and C, we have the same 120 volts. Now, between like here, this point here, let's say that this is point C or close to point C, and this positive terminal here, we still have 120 volts, okay? Now, what you are going to do when you solve this circuit is that you are going to use what is called additive and subtractive polarity, okay? But with your current, not only with your voltage, but with your current. So I'm gonna explain that to you just now. So let's say that in a circuit, we have the following. If we have, okay, that vector is gonna represent current. If I have that little vector there, and that represents 5 amps,
And then I have a second source, a second vector. Okay, so I'm gonna do the following. I'm just gonna draw like a little node, a connection point like this one here. So if I have 5 amps that goes into that node and have another 5 amps, or no, let's say this is 10 amps. That goes into that node. If I ask you, what is the resultant current coming out? Would you be able to tell me how many amps we have on this vector here?
Would it be 5?
Okay, so you have 5 that come in and 10 that come in. So how much is going to be getting out?
15.
15 by all means. Perfect. So when you are solving this circuit here, it's going to be the same concept. Okay, you are going to have to keep in mind that the flow of current here is like this. That's going to be one vector. And this one goes like this. That's going to be another vector, right? Now, the flow of this one is going to be like in this direction. It's going to be an opposing vector. Okay, so that being said, the value of this current is going to be subtracting to the value of this resultant current that is coming this way, because they are in opposite direction. So if I had like the 5 amps in this direction, and I have another vector, okay, like that is in the opposite direction. If both of them, like, and this is representing current flow, okay? So in that instance, then we have, like, if this is 5 amps, and this is 5 amps as well, and they are in opposite directions, then the resultant current that I'm going to have right here on the vector itself would be equal to 0. Now, if I have, like in this instance here, what we have is a what? A node. And what I want to emphasize by this node is Kirchhoff current law, which is the same thing that we were seeing before, that if we have like the sum of the currents in a circuit is always going to be equal to the total current. So Kirchhoff current law dictates that the algebraic sum of the current that enter and leave a node is always equal to 0. In other words, is what I told you. So the sum of the currents that come in is going to be equal to the resultant vector that goes out. Okay, now if we have a junction point like this, and we have current in 2 different directions, they are going to be fighting each other because they are in different directions, and the resultant current is going to be equal to 0 in that case. So you are going to be using this idea in order to solve for the values of current in this circuit. So other than that, guys, so please take, please now, we only got like 20 minutes left and I didn't give you a break, a second break. So please take the time. Take the time to start going through your Monday work, you know, which is city circuits, and also like start getting into parallel circuits. Once you do that, once you finish city circuits, please make sure that you go to this quiz and you do this quiz. Remember, this quiz is not full marks. It's just to get you ready to write that not the midterm, to write your term exam, which is like full marks. It's going to be 25 points. I put a lot of emphasis on circuits. So once you do that, please make sure you go into parallel circuits as well. And once you finish your handouts for parallel circuits, please do the quiz as well. Okay, that's why that it says here that it's going to start on the 10th, because I don't want you to jump into parallel before you master series. And next week, then, with this knowledge in the back of your mind, you know, with these tools already with you, then we are going to be able to do week 4, which is combination circuits. And that's a big one, okay? Like combination circuits is very, very important, because everything in the field at the end of the day is connected in a series parallel layout, in a series parallel arrangement. So without further ado, like, well, I'm not gonna continue giving you more information for today. So the time is yours. Feel free to, I mean, like, play with this, work among you. And if you have any questions, then send me an email. Okay, so to see how much I can help you through this process of learning. So I'm gonna set from now the time these circuits, combination circuits, is gonna be available. I'm not gonna make it available right away. So it's gonna be available on the 15th. Okay, like another 15 is gonna be available actually like at the end of this week, the 12th. Okay, and if you want, you can go ahead and start browsing that topic. So, any questions before I let you go?
On the test in 2 weeks there, is there going to be questions from like the test we just did, or is it just questions from this week and next week?
This week and next week only.
Thanks.
Yep, you're welcome. So there's an announcement here. You don't have it yet because that announcement is going to be posted like on the 12th. That says that the topics for the test is only series and parallel. Can you see it there?
Yeah.
Yeah, so what happened is that you just finished a test, and that's why I haven't released the announcement, but it's going to be released on the 12th. And it's going to tell you that you have, that it's going to be Friday, February 19. It's going to be from 6, just like before, to 11:30 at night. You're not going to have a time limit. I mean, if you open it at 6 in the morning, you can close it at 11 at night. That's fine. You can spend the whole day like doing your test. And the location is going to be online, of course, and it's going to be based on series and parallel and combination circuits. Anyways, guys, so have a good one and have a nice rest of the week.
Thank you.
Thank you.
You're welcome. Have a good one. Thanks to you guys as well.
Thank you. Bye.
Bye-bye. Thanks.